Hello everyone, my name is Pavya Soni and my number is 18 MCEN 14. Today's my topic is branch and bound technique for 01 knapsack problem. Let me introduce the technique first, branch and bound. Branch and bound is a technique for exploring an implicit directed graph. The graph is usually acyclic or a tree. This technique is used to solve a problem in optimized way. It will give the optimal solution of the given problem. At each node, we calculate a bound on the possible value of any solutions that may lie on the graph. Calculated bound is used to choose which open path looks the most promising, so it can be explored first. A BFS breadth first search technique explores nodes in the order of their creation using a queue. Branch and bound uses BFS technique to solve a problem. Now, let's see what is knapsack problem. The problem statement is given as given two integer arrays value ranging 0 to n minus 1 and weight ranging 0 to n minus 1 that represents values and weights associated with n items respectively. We have to find out the maximum value subset of a value such that sum of the weights of this subset is smaller than or equal to knapsack capacity W. Maximum capacity of knapsack is W. We can either choose or not choose an item. We have x1, x2, x3 up to xn items where xi belongs to 0 and 1. If value of xi is equal to 1, then item x is selected, and xi is equal to 0, then item is not selected. Our main objective is total gain value should be maximum. Now I am going to explain 01 knapsack problem using branch and bound method. Here are the procedure steps to solve the problem. It consists of basically 5 steps. This algorithm sorts all items in decreasing order of ratio of value per unit weight. We will be using greedy approach so that upper bound can be computed. For this algorithm, we cares about maximum profit. For that, we have to initialize it with 0. So, the second step will be initialize maximum profit to 0. As BFS using queue data structure, we need an empty queue. So in third step, we will create an empty queue named queue. And the fourth step is to create a dummy or a root node of decision tree and enqueue it to the queue. profit and weight of the dummy or root node are 0. We have to repeat this following steps until Q is empty. We will now start extracting items from Q and let it named by U. Now compute profit of next level node. If the profit is more than maximum profit, we have to update maximum profit. In next step, we have to compute bound of the next level node. If the bound is more than maximum profit, we have to add next level node to the queue. Now consider a case when next level node is not considered as a part of solution and add a node to the queue with level as the next level, but the weight and profit without considering next level nodes. Now we will see the algorithm with an example. Now I am going to explain one example of 0-1 knapsack problem using branch and bound technique. Here we have 4 items, item 1, 2, 3 and 4, with values 10, 10, 12 and 18 and weight 2, 4, 6 and 9. Maximum capacity of knapsack is represented by W. Here the value of W is 15. Now as per the algorithm, we have to calculate value by weight ratio and we have to sort the items in decreasing order according to this ratio. Now let's calculate V by W ratio. Here 10 by 2 is 5, 10 by 4 is 2.5, 12 by 6 is 2, 18 by 9 is again 2. Now we have to create a dummy root node and weight of root node is 0, value is 0. Now we have to calculate an upper bound of this root node. Let's name A and let's calculate upper bound of A. Here we have to consider a greedy approach to calculate upper bound. So first we will consider item number 1 with value and weight. Value of item 1 is 10, weight is 2. Item number 2, value is 10 and weight is 4. We have to take care that our weight should not exceed 15. Now let's take item number 3, value is 12 and weight is 6. Now we have weight 12 and here the weight is 9. So we have to take a fractional part of that. So we will take 3 units of item number 4, which will have a value 2 into 3. So the upper bound will be 10 plus 10 plus 12 plus 6, that is 38. Now we will create two leaf node that item 1 is selected and item 1 is not selected. Now let's name this leaf nodes to B and C. Here we are considering item 1, so the weight will be updated by 2 and value will be updated by 10. Now again we have to calculate upper bound for the node B, which will be same as upper bound of A. Now here we are not considering item number 1, so the weight and value will be same, so weight will be 0 and value will be 0, and now we have to calculate upper bound. Now so upper bound for C, here we have to value and weight. We don't have to consider item 1, so we will start with item 2 having value 10 and weight 4. Then item 3 having value 12 and weight 6. We have here 10 units of weight, so we have to take fraction part of the fourth item. We have to consider only 5 units of weight, so the value will be 5 into 2 of item 4. So the upper bound will be 10 plus 12 plus 10, which is 32. Now we have to explore the Now we will further explore node B that have two child nodes named D and E. Here let's consider item 2. Item 2 is considered, item 2 is not considered. If we consider item 2, then weight will be 2 plus 4, that is 6, and value will be 10 plus 10, 20. And upper bound will be same. If we don't consider item 2, then weight and value will be as it is, so W is equal to 2 and V is equal to 10, and we have to calculate upper bound. So upper bound for node E will be, here we are not considering item 2, so item 1 having value 10 and weight 2, we are not considering item 2. Then item 3 having value 12 and weight 6. Here we have 8 units of weight and we have to make it 15. Now we have to calculate upper bound for E. Here we are not considering item 2, so the upper bound will be calculated as item 1 and weight 10, value 10 and weight 2, item 3 value 12 and weight 6, and item 4 weight 7 and value 14 according to that. So the updated upper bound for node E is 36, that is 10 plus 12 plus 14. Here we are getting maximum upper bound here, so we will explore further nodes. Let's name them F and G. Now here we are considering item 3, and here we are not considering item 3. If we consider item 3, then weight will be 6 plus 6, that is 12, and value will be 20 plus 12, that is 32, and upper bound will remain same. If we did not consider item 3, then weight and value remain same, and we have to calculate upper bound for node G. Now to calculate upper bound for G, we have to consider only item 1, 2 and 4, which are having values 10, 10 and 18, and weights 2, 4 and 9. So we will get upper bound as 38. Now let's further explore the node F. Let's name H and I. Here we are considering item 4, and here we are not considering item 4. If we consider item 4, then weight will be 12 plus 9, which will be greater than 15. So we cannot consider item 4. Now let's not consider item 4. So weight will be 12 and value will be 32. And upper bound for node I having item 1 plus item 2 plus item 3, which are having values 10 plus 10 plus 12 and weight 2 plus 4 plus 6. Here we are having weight 12 and value 32 and upper bound as 32. Now here our weight is less than the capacity of knapsack. We have another option, that is node G. We have to explore them. Let's consider here item 4 and here not considering item 4. If we consider item 4, then weight will be 6 plus 9, that is 15, and value will be 20 plus 18, that is 38, and upper bound for the node J is 38. Here we are getting same values of upper bound and value, so this will be our optimal solution. Now let's trace the path that we are considering which item and which item we are discarding for the maximum capacity and maximum profit. So we will include, so solution will be item 1 will be considered, item 2 will be considered, item 3 will not be considered, and item 4 will be considered, and maximum profit will be 38. So this is our end of the example. Now we will take example 2, in which we have total 5 items having values 30, 20, 100, 90 and 160 and weight 5 10, 20, 30, 40. We have maximum capacity of knapsack is 60. As discussed in algorithm, we have to calculate V by W, that is value by weight ratio, and arrange the items in decreasing order of this ratio. So here we have already calculated that ratio and arranged the items according to the decreasing order of the ratio. Now let's take the solution. We have to create initially a root node having weight 0 and value 0. Now to calculate upper bound of the root, let's take item 1 having value 30 and weight 5, item 3 having value 100 and weight 20, and item 5 having value 35 into 4 and weight only 35, because we have to take only capacity of 60. So the upper bound will be 270. Now if we consider item 1, then weight will be 5, value will be 30, and upper bound will remain same. If we do not consider item 1, then weight will be 0, value will be 0, and we have to calculate upper bound for the node B. So upper bound for the node B is, consider item 3 having value 100 and weight 20, and item 5 having value 160 and weight 40. So our upper bound will be 260. Here we have maximum value of upper bound at node A, so we will explore node A with considering item 3 and not considering item 3. If we consider item 3, then weight will be 5 plus 20, that is 25, and value 30 plus 100, that is 130, and upper bound will be same. If we do not consider item 3, then weight and value will be same as the root, that is 5 and 30, and we have to calculate upper bound for the node D. So upper bound for node D is, considering item 1 having value 30 and weight 5, item 5 having value 160 and weight 40, and item 4 we have to take only 15 units of weight. So the value for node D, that is upper bound for node D, is 30 plus 160 plus 45, that is 235. Now here we are having maximum value of upper bound at node C, so we will explore node C further with considering item I5 and not. If we consider item I5, then weight will be 25 plus 40, so it will exceed the capacity of knapsack. So here we will not consider item I5. If we do not consider item I5, then weight will be 25, value will be 130, and we have to calculate upper bound for the node F. So upper bound for the node F, we will consider item I1, I3, I4 and some part of item I5 having values 30, 100, 90 and 10 respectively, and total weight will be 60. So upper bound for the node F is 230. Now we are having 230 235 and 260. Whichever upper bound is maximum, we have to explore them. So we will explore node B further with considering item I3 and not considering item 3. If we consider item 3, then weight will be updated to 20 and value will be updated to 100, and upper bound will be same. If we do not consider item I3, then weight will be 0, value will be 0, and we have to calculate upper bound for node H. So upper bound for node H is item I5 plus I4 having weights of 160 and 60, having values 160 and 60, so upper bound will be 220. Now here we are getting 260 as a maximum upper bound, so we will explore this node further with considering item 5 and not considering item 5. If we consider item 5, then weight will be updated to 20 plus 40, that is 60, and value will be 260, that is 100 plus 160. And upper bound will be remain same. Here we are getting value and upper bound as same number, so this will our final solution. So in final solution we considered item I5 and I3 having maximum value of 260. So this will be our optimal solution for the knapsack problem. Thank you.